Few final comments related to seismic loads. Well, first, do you all have any questions for me based on the last couple of lectures? So last time we went through this example of determining the seismic loads on a low-rise structure here. And I kind of broke it into three parts, right? First part was to determine design earthquake and seismic design category. Second part was to determine the seismic forces, right? So that's your base shear, and then distributing that base shear up the height of the building was the last step, right? So that's the part three, vertical distribution. And we talked about how with that design earthquake, right, the response spectra looks something like this, right, where you've got on the horizontal axis, right, that's the natural period of the structure, and on the vertical axis, it's some measure of acceleration response. So for the design earthquake, it would be like your response parameters, right? So you've got the SD, S, and the SD1 value showing up here. All right, so the entire spectra here represents the design earthquake response. A lot of times we just shorten that and say it represents the design earthquake, but it's important to remember that the response of the building, right, the acceleration with which the building responds to the earthquake is different from the ground acceleration or the acceleration of the actual earthquake. So I just wanted to clarify that. And the design spectra is simply 2/3 of the maximum considered earthquake, right? So if you can imagine whatever that looks like, it would be a larger magnitude. Now the maximum considered earthquake is what we would use for certain other dynamic analyses. So remember we talked about how this static approach is appropriate for most buildings, and that's why we're teaching it in this class. It's also the most, it's the most commonly used method anyway, and it's the easiest one to teach and present in a class. That said, right, there are certain circumstances when we can't use that method and we have to use a more accurate dynamic analysis. But those dynamic analyses are a lot more complicated, they're more involved, they're a lot more expensive because they take a lot more computer power, right? But I just wanted to kind of show you for reference what is really the difference between the maximum considered earthquake and the design earthquake with regards to what it means for the structure. Because remember, the goal is to design the structure so that it survives a major earthquake, but we understand that there may be significant damage sustained. So I'm going to switch for a second over to DocCam because I don't have this slide on the iPad. And this chart here just shows you the different levels of earthquakes that we use for design. So MCE, the maximum considered earthquake, is shown down here. The design earthquake, which we are focusing on in this class, we use that for the ELF method, is here. And then the frequent earthquake is up at the top. So the frequent earthquake would be what we would use for assessing serviceability performance of a building, like, you know, can the building still function? And here it shows you the level of expected performance, and that's tied to risk category, right? So for a frequent earthquake, you would want a risk category 4 structure, which is, you know, those essential facilities, to be operational for sure, right? A risk category 4 building in the design earthquake should be able to be immediately occupied after the event, right? So we definitely want those to remain available to people for occupancy. At the maximum considered earthquake level, we would design those risk category 4 structures for a life safety level, right? For risk category 2, which is your ordinary structure, and also risk category 1, So in seismic design, risk categories 1 and 2 are treated the same. You would want immediate occupancy following a frequent earthquake, right? For the design level earthquake, you would design that for life safety. And then in the maximum considered earthquake, you're just trying to prevent collapse, right? So the way that these earthquakes are actually determined, right? Because remember, we pull those values from the map and then we adjust it based on the soil at the site to get the maximum considered earthquake. And then we take 2/3 of that to get the design earthquake. So really it's coming from those mapped values. So what do those represent? Those mapped values represent a response of the building to ground motion that's expected at the site, right? And so your maximum considered earthquake, once you adjust it for the site conditions, the soil at the site, it represents an earthquake that has only a 2% chance of being exceeded in 50 years, right? And your design earthquake represents a magnitude that only has 10% probability of being exceeded in 50 years. So that's where all that comes from, and this is really background information. It's not something that you need to know for this course, but I think it's helpful to provide that kind of context. So, yeah, any questions there? Okay. All right, so let's see. I don't know if I had anything else. I think this was included in the first lecture. This is just showing Minnesota with no earthquake requirements. We saw this as well. This was tied to the New Madrid fault, and here these are also showing the New Madrid fault. So I don't know if these were shown before, but this is just showing, you know, all the seismic activity within a period of time. I don't remember what period of time that is, and I don't think my notes say it. But you can see, you know, it's a pretty active region right there, and it's right there along the border of Tennessee and Missouri up to southern Illinois there, and Arkansas. I think that's Arkansas there. So yeah, and again, I already said this a couple times, but we talked about the effects of that. One other thing that I think maybe was mentioned in the recorded lecture, but I didn't mention the other day. Folks reported seeing lights flashing after this earthquake. There were a lot of like weird phenomena that they didn't quite understand that was associated with this earthquake. And I certainly don't mean to make light of the event, because it was very serious. An entire town was destroyed and a lot of people lost their lives. But it does remind me that there's still that phenomena that is not fully understood of lights flashing in earthquakes, and that has been observed since then in other locations like Mexico. So I think I actually have a video up ready to show you guys on that. Let me double check there. We'll take a look. So I think it's here we go. All right, so we'll just take a
On the
quick
night
look
of
at this
September
video.
7th, a magnitude 7.0 earthquake rocked southwest Mexico and ricocheted across social media. Online, people posted about strange flashes in the sky at the time of the earthquake. The hashtag Apocalipsis gained traction. What exactly was going on?
I felt the earthquake very strongly here in Mexico City.
As a seismologist, it's a cool thing to experience.
During some part of the earthquake, it's difficult to walk.
I could feel like how violent the movement was.
The quake's epicenter was near Acapulco on the west coast, but it rattled Mexico City about 200 miles away. At the time of the quake, many reported seeing these flashes.
Yes, I saw the lights, of course.
There's some disagreement as to the cause of this light, however.
During the earthquake, we were having a thunderstorm.
So maybe the flashes were lightning, at least in part.
I saw the flashes in the street produced by electric arcs because of the movement of the cables, of the power lines.
Others posted videos online that showed transformers exploding, which could have been another source of the light. But there are other kinds of earthquake lights, not caused by lightning or transformers. They're white flashes that accompany or precede large tremors, especially in certain places, like this one in Japan. And scientists say they're real.
But they're not understood.
Here's what we think is going on. It's basically static electricity. Charge appears to build up within the Earth's crust, which then gets discharged into the air, creating a visible spark. It's the same for any accumulation of electrons. Like if you shuffle along a carpet in socks, touch the doorknob, and feel a shock.
You are generating a strong voltage between your finger and whatever happens to draw the spark.
Same thing when clouds in a thunderstorm discharge lightning to the ground. This rapid movement of electrons produces light. When it comes to what's creating the charges that may be responsible for earthquake lights, there's one thing folks agree on.
Nobody knows. So,
There are a few theories. Theory number one.
underneath the earth, there's huge pressures, and you grind things against one another.
Put certain kinds of rocks in a vise, clamp down, and you produce a voltage difference across the stone. Maybe that's what leads to the sparks. Or maybe it's the friction from all that grinding. Another theory is something called fractoluminescence.
So the act of making a fracture produces light.
And naturally, earthquake activity fractures rock as the waves ripple through the ground. Troy Shinbrot has another theory that comes from his efforts to understand earthquake lights in the lab using a tumbler filled with flour.
We did the simplest, dumbest experiment, and we seemed to see something.
Tip the tumbler slowly, and at a certain point, the flour slips.
Before it slips, you can see there's a little crack that appears, and this crack generates measurable voltages. And then because there is this crack, the grains that are sitting on this unsupported region start to slip. Earthquakes are on a much larger scale, where the granular bed is the entire earth underneath us. And the idea is that this crack generates a voltage that is of such a large magnitude that it produces earthquake light.
Now, we don't know whether any of the flashes during the recent Mexico quake were indeed earthquake lights, caused by this discharge of static electricity from the movement of the Earth. And if they were, we don't have the data to know what force or stress within the Earth produced them. Shinbrot wasn't there to document them, and Miguel Santoyo is skeptical.
It's not very probable that we have seen that kind of light so far from the epicenter here in Mexico City.
So stand down the apocalypse alerts, but maintain the early earthquake warning alerts, because the ground will continue to shift beneath us.
This is where we live, and we need to live with this, and we need to be ready every day of the year.
All right, so I just thought that was just pretty interesting. They still don't fully understand what's going on there. Not directly related to structures, but just some cool context there. So I also had a few other earthquake-related things. When I was in graduate school, one of the outreach activities that we did with EERI, which is the Earthquake Engineering Research Institute, was to give various events. Had a shake table, a small shake table, and we would have kids build structures out of Legos and or K'NEX, and then we would test them on the shake table to see how they would perform differently, and they'd form in teams and compete against each other. Generally speaking, depending on what we were, what our goal was and how long the activity lasted, we would compare the K'NEX to the Legos and demonstrate, this is a difference between a tall, flexible structure moving in an earthquake, and then Legos would represent a shorter, more brittle structure. So you could see the swaying and the dynamic motion much more of the tall earthquake made of, or the tall building made of K'NEX. I think this video just uses Legos, and that was the more fun one actually to show. Oh wait, is this even what I think it is? Sort of. Okay. Well, there we go. That's the fun part, watching them fall. So the kids would all cheer when the Lego towers collapsed, but we judged them on, aesthetics and efficiency, the cost and then how long it lasted in the quote earthquake and things like that. And then kind of along those lines, on the topic of Legos and back by popular demand, see what happens with a whole bunch of Legos under the hydraulic press.
For about
Oh, if we can skip this.
it's new
Maybe not.
you compostable zipper bags and give you free trash bags for
Welcome to the hydraulic press channel.
Okay. So, this is a long video. I might have to jump around to find the good part. I had it queued before, but I don't remember where. Oops. Okay, where were we?
Oh, it's going to explode.
I think that was just a solid block of Legos.
Okay. It didn't explode.
Oh, that's just slow-mo. Looking at the damage.
Kind of stopped, but also the Legos got messed up.
A Lego pancake.
Yeah, so I would say that now it's even. The press didn't completely win, but the Legos didn't either. So we are going to do a third round.
Let's see. Anything better on here?
2 hours with 3 people. So a lot of work also. That it bends only I think I calculated that it bends 1 millimeter or something like that.
Let's see. Oh, okay, well, all right.
I
we'll
took
watch a little more.
the Legos are where the the Legos are where the sensor was.
There is no sensor, that's why it doesn't work.
As a victory for the Legos.
Is that a victory for
I
the
think
Legos?
purple bricks, you can see that there is lighter sections that are deformed slightly. But
Oh,
in
yeah, you
general,
can see the deformation.
I'm
that's
going
what
to
he's talking
say
about.
that the Legos win and the press lose. Because it didn't go
All right, well, that's good enough for today, but thought I'd throw that in there. So, all right. So wind loads. The wind load lectures will be starting off with these skeleton notes and then shifting to, once we finish these, which won't be today, we'll finish these skeleton notes on Monday. Once we finish those, then we'll start going through the code or the standard tables and figures, and that I have taken care of in the PowerPoint presentation, so the slides will be relevant to that portion of the wind loads lectures. So I'd have both ready for Monday, because I expect we'll definitely start the PowerPoint slides on Monday that will take us through the ASCE 7 specific tables and figures. So today we're just going to start with talking about the basics of wind loads, the concepts, and basic applications. So wind loads, and I'll have some more fun things to share with you regarding wind loads later as well. Wind loads are also a dynamic force that acts on a structure, right? It's like seismic loads. But also, like seismic loads, we have simplified methods that we can use for most buildings that treat it as a static load. And that's what we're going to be learning in this class. So essentially, when we think about wind interacting with a structure, right, it's just going to be passing around your structure, so all the external surfaces are affected, and what the building feels on those surfaces is pressure, right? So we apply wind loads as a pressure acting over a surface. We have positive pressures, which are always pushing towards the surface. And we have negative pressures, which represent suction and always act away from the surface. All right, so these loads, as I mentioned earlier, we assume them to be static for most of our analyses here. In reality, they are continuously changing. So there are two general analyses that we always consider for structures. The first one is the overall structural response to wind. And this is what we call the main wind force resisting system, or MWFRS for short. This one is used to determine the required strength and stiffness of your lateral force resisting system. So your braced frames, shear walls, moment frames, whatever you choose, right? In this analysis, we have to consider both positive and negative pressures. And we also need to consider multiple wind directions. The second analysis that we always need to consider for buildings is for the local structural response. So we call this components and cladding analysis, or C&C. This is used to determine the required strength and stiffness of wall and roof elements and their attachments to the building. So the roof and wall elements that we're thinking about, these are the coverings, right? You can think of it as the skin of the building, because those are the elements that are basically on the front lines of defense for the building with regard to wind. So they're gonna feel all that pressure first, and then they're gonna transfer it to the rest of the structure. And so because of that, the pressures that we use to design these components and cladding elements are typically higher than the pressures we use to design the main wind force resisting system and the lateral force resisting systems. The reason for that is because we don't want those components and claddings to fail, right? We want them to be able to function and transfer the forces to your lateral force resisting system. So we design them for higher pressures. Say larger, usually larger. Now in this class, we are going to focus on the main wind force resisting system analysis. The only thing you need to know about components and cladding are the two items noted down here, right? And then the comments associated with the sketch there, right? So the conceptual application of it. So let's say that's the focus. All right, so the little sketch below kind of demonstrates, a representation of what the actual wind effect on a building might be. So the first wall that it encounters will experience a positive pressure, right, acting towards the surface, and it's going to fluctuate, right? It's not going to be a perfect curve or a line. It's going to be constantly changing with time. On the roof, if you have a flat roof, that's going to experience negative pressures, right? That's also going to fluctuate in magnitude. And then on the far side of the building, right, so the wind is wrapping around all three surfaces and it's going to reconvene on the other side, that's going to create suction on that far side. We call that the leeward side, and we'll talk more about that on the next page. But that side is going to fluctuate also, but it's going to be sort of constant. It's going to be more constant than the windward side and the roof. So for our main wind force resisting system analysis, we simplify these distributions, right? So in theory, we simplify this windward wall as a linear variation with height. In practice, though, we further simplify that and break it into blocks, right? So it might look something like this in practice. Let's see. All right, and so I'll just note that in practice, we use blocks. And we do a similar approach for the roof, right, to represent the trend of decreasing magnitude along the length in the direction of the wind. And then we simplify the leeward side as being a constant distribution with height. The components and cladding pressures, right, we treat them as localized pressure distributions. And this is simplified as well, so we would have similar, right, application on the roof. So I'll just add a few notes here. This is simplified and local. All right, this is simplified and global, all right, for the overall structure. And the actual have instantaneous pressures. All right, so on the next page, we've got, we're going to break down a few characteristics of wind. So first, the wind velocity, right? The wind velocity varies with height above the ground. If we were to sketch a profile, right, where this bottom line represents the ground, the wind velocity would take on the form of a parabola, something like this, where above a certain height, we call that gradient. Let's say that occurs around 1,200 feet. All right, the wind velocity above that level is constant. So we call that gradient velocity. And at the ground, the wind velocity is 0. And that's due to surface friction. All right, so that would be the direction of wind flow in this representation. Wind is also very turbulent in nature. So turbulent is a word I threw on that seismic quiz. Turbulent would not be appropriate to describe seismic loads because the definition of turbulence is a violent or unsteady flow of air or water or some other fluid. So with air, since air is a fluid, right, it's actually quite turbulent, and that means that it can become turbulent at about 2 to 3 miles per hour. So, and that's tied to its viscosity, right? So air has a much lower viscosity than water. It's about 1/16 that of water, in fact. And so that's why it becomes turbulent at very low speeds. So I'll note very low viscosity. This is affected by the surface roughness, right? So the ground roughness in the area will impact turbulence. And that turbulent nature tends to generate gusts. So you can have very large gusts, and they will act in concurrence with smaller eddies. And so the effect of that is really a dynamic response on the structure on the structure's part. And we account for that in our static analyses by using a gust effect factor. And so we'll define that gust factor later on in the wind loads lectures. All right, so based on what we just described turbulence as, quick question, is turbulence a force? What do you think? No, right? Yeah, it's not. Actually, the reason I asked this question is because I always remember this years and years ago. I don't know if you remember, or maybe they still have this show, It was, I don't remember what it was called, but it was the show, it was a reality show where people would step into a taxi and the taxi driver would have questions for them, like trivia questions, and if they answered them right. Yeah, Cash Cab, good, yeah, thank you. So I remember watching a Cash Cab episode one time, and one of the questions was, it was something along the lines of like, which of the following is a force? And I think turbulence was one option and drag was another option. And there were a couple other options thrown in there. And I remember they responded with turbulence, and I was like, nope, definitely not, it's drag. So, yeah, so turbulence is not a force. Drag is a force. So, all right, so moving on. Different types of wind that we need to think about. All right, there are straight line winds. Thunderstorms can generate certain unique types of wind, specifically downbursts. And then hurricanes are essentially extreme straight line winds. We'll talk more about that in a moment. Tornadoes, last but not least, those have the highest wind speeds. So the straight line, going back to that, is the most common. All right, we've all experienced straight line winds. Thunderstorm can generate downbursts. So this is an event where air pressure differentials or temperature differentials generate pressure. Differences in temperature will generate differences in pressure, or, they're linked, and that will cause the air to flow swiftly down and out. And this can be so forceful that it can shatter cladding on tall buildings. That's been known to happen. It can also flatten trees. So there was an event several years ago in the Tobacco Root Mountains. I think they called it a microburst, but it was basically a downburst that flattened like 200 to 250 acres of trees in the Tobacco Root Mountains. And I have a picture to show you later of that. So it can be pretty powerful. With hurricanes, right, as I mentioned, we treat them as extreme straight line winds. So even though hurricanes rotate about the eye, right, I don't remember exactly, I think it's counterclockwise above the equator and clockwise below the equator, or maybe I have that backwards, I don't remember. But anyway, they do rotate a certain direction about the eye of the storm. But because the diameter of the earthquake is so large, as far as a specific building location is concerned, that building is experiencing a straight line wind. Right? Now that direction of the wind might change as the hurricane moves location. So depending on where the building is with respect to the center of the storm, or et cetera, that direction that it experiences will change, but it's basically a straight line wind by the time it hits the building. And then tornadoes. These have the highest wind speeds of all, or they have the potential for the highest wind speeds. And so far, right, up through the current version of the standard that we're using, that's been adopted into code, the ASC 716, tornadoes have only been addressed in the commentary of the code, so it's not really implemented as requirements through the standard. But that will change in the next round. So ASCE 722 introduces a whole chapter on tornadoes and tornado loads. And so that's, again, that document is a work in progress. It's a living document, and we're constantly adding new information. All right, so now we'll describe wind flow around a building. We already talked about this a little bit on the previous page. For a given wind direction, all right, and we typically consider wind perpendicular to each face. And those would be separate analyses. So for most buildings, right, that are somewhat regular in plan like this, a rectangular shape, for example, you would really only need to consider two different direction analyses. One for the east-west wind and one for the north-south wind. So the wind in this direction will have the same overall effect as the wind in that direction, and so on. But once we've identified the direction of wind that we are evaluating, we need to identify the different surfaces of the structure with respect to that wind direction. So the windward wall is always the first surface that the wind will encounter, right? And that's always going to have positive pressure. And it's always going to vary with height for the reason that we noted above with the wind speed varying parabolically with height. All right, so the wind will approach the building. That windward wall provides an obstacle, so it has to find a way around it. So the flow will separate at the corners and reconvene on the other side. It will also, this is a plan view, right, this sketch, but it will also flow up and over the roof and then back down to the other side. So we'll label our windward wall over there. There's the leeward wall, and then you have the side walls here and here. The leeward wall is always opposite the windward wall. That will always have negative pressure, and it will be treated as constant with height. The side walls, you think those will be positive or negative pressures? What does your gut tell you? Positive?
Yeah. Negative.
Negative? Who thinks positive? Who thinks negative? All right, negative is correct. So if you think about, right, the wind separating at the corner, right, that's going to basically create a vacuum here. It's going to create suction around right at the surface of that wall. So side walls will have negative pressure, and we also treat that as constant with height. All right, now the roof is a little bit more complex. So the roof, it depends on if it's a flat roof or if it's a sloped roof, if the wind is parallel to the ridge or perpendicular to the ridge, where, if, ridge applies if it's a sloped roof. So to kind of just break it down into, a few basic concepts, the windward side of the roof, if you have a sloped roof, it will have either positive or negative pressures, right? So it could be either one if it's steep. If it's a shallow roof, then it will have negative pressure, right? Negative pressure if shallow. The leeward side, if you have a slope, will be negative pressure and constant. And the sides, if you have a sloped roof or a ridge and so on, will have negative pressure and will be treated as constant. A flat roof will always have negative pressure. And the pressure magnitudes can decrease with length in the direction of the wind. Right. So then one other thing I want to point out on this sketch before we go on to the next page In the plan view here, I've noted the dimensions of the building as B and L. So this is specific to wind load determination. Okay, one moment. Let me finish this thought here. So B is always the dimension perpendicular to the wind. And L is always the dimension parallel to the wind. Okay, yes, your question?
So if there were alleys on the sides of the building, would the pressure be positive?
If there were alleys,
Be-
yeah, so between two buildings, you'd have suction. So it would kind of create a wind tunnel effect, actually. But the effect on the buildings we would still treat it as negative. But that's an interesting point that you raised because the wind structure interaction can be affected by other buildings that are surrounding it. And so for that reason, buildings that are in urban areas are often not low-rise buildings really, but especially for taller buildings, we don't use this approach anymore. We use a wind tunnel study where they create a scale model of the building and all of its surroundings for like hundreds of feet around it, so that we can get a feel for how those extra structures and maybe a tall building before it can cause, if it's upstream of the wind direction, right, it can cause some peculiar effects like buffeting, where the wind just kind of pounds on the building behind it. So we use wind tunnel studies to account for things like that, yeah. But yeah, so to go back to your exact question with alleys in particular, it would still be treated as a negative pressure on the building, yeah. And wind tunnel studies have shown this, yeah. Good question. Others? Yes?
By shallow, do you just mean like less slope of roof?
Yeah, so the exact definition, the exact cutoff is 10 degrees. Yeah, and I think we look at that on the next page. Yeah, any other questions? Okay. Oh, well, looks like we're about out of time. So this is a good stopping point for today. Next time we will continue with wind structure interaction and discussing external and internal pressures, and then go on to defining the net design pressures. And then we'll dive into the ASCE 7 handout. So before y'all take off for a second though, just a quick reminder, right? The assigned reading is contained in this handout here. So the section on wind loads, I think, is the longest one in this entire handout, but it's packed with information. So definitely, be sure to read this. It's pretty much what I say in lecture plus a little bit extra, minus the figures and examples, but it's packed with good information and it's pretty well organized. So, all right, don't forget about it. All right, well, thank you all. Have a great weekend. See you Monday. Oh, I will be posting homework 7 probably today, so keep an eye out on that.